Dear friends, myself Dr. S.B. Sawarkar, Professor Department of Physics, Sri Shivaji College, Akola. Today I welcome you all in our 9th lecture. In this lecture, we will study relativity of mass, that is variation of mass with velocity. According to the special theory of relativity, the mass of the body does not remain absolute. The mass of the body is found to be more in a state of uniform motion relative to its mass at rest. Let us consider two inertial frames of reference S and S dash. Frame S is at rest and S dash frame is moving with uniform velocity v along the positive direction of x-axis in such a way that their x-axis remain parallel. X and x dash axis are parallel. In this case, now let us consider two balls, identical balls A and B. This ball A is placed in the rest frame S here and ball B is placed in the moving frame S dash. Both these balls are the identical balls. At proper time, this ball is thrown vertically upward and ball B is thrown vertically downward. The collision between the balls A and B will take place at a proper time, and after collision, ball A will move vertically downward and ball B will move vertically upward. Now, the observer in the frame S observe the motion of the ball A. With respect to the observer in the frame S, the ball A will move first vertically upward and then vertically downward. But motion of the ball observed by the observer in the rest frame S will be the parabolic before and after collision. And collision which will take place here, it is a perfectly elastic collision. It is a perfectly elastic collision between these two balls. And the appearance of the motion of the balls A and B for balls B and A will be similar for an observer in the moving frame of reference S dash. Let VA is the velocity of the ball A with which it is thrown vertically upward and it is observed by an observer in the rest frame S, and VB dash is the velocity of the ball B which is thrown vertically downward for an observer, and it is observed by an observer in the moving frame of reference S dash. And let us assume that VA equal to VB dash. Let it be equation number 1. The after collision, the two balls rebound. The ball A vertically downward and B vertically upward. For the observers in the frame of reference S and S dash, let this small d is the distance between the x and x dash axis. As VA equal to VB dash, these velocities are equal. VA equal to VB dash. The collision between the ball will take place at a distance equal to d by 2. This distance is d, and collision will take place at the center, that is at a distance d by 2. Here, let t0 is a time taken for the round trip of the ball A in the S frame, which is called the proper time, and it is given by t0 equal to d by A. D total, as here distance travelled by the ball, say ball A, while going up it is d by 2, while coming back it is d by 2. So d by 2 plus d by 2, it will be d. So total distance travelled in the round trip of the ball A, it will be d divided by its velocity, which gives us the time, which is called time taken for the round trip of the ball A, which is called proper time. Since VA equal to VB dash, for an observer in the moving frame of reference S dash, the observer in the S dash frame will observe the same time t0, which is the proper time for the ball B, and so t0 will be equal to d upon VB dash, d upon VB dash. Since the ball B is in uniform motion, relative motion, with respect to the observer in the frame S, this time recorded by him for the round trip of the ball B will not be same t0, but it is t. So the time recorded for the ball B by the observer in the S frame, which is relative time, and as per the principle of the time dilation, we can write this relative time t equal to t0 upon under root of 1 minus v square by c square. Similarly, the relative velocity of the ball B with respect to the observer in the stationary frame here, it will be, say, represented by, say, VB equal to distance travelled is d and relative time is t, so d by t. Let it be equation number 4. The law of conservation of the momentum is true for all inertial frames of reference. If the masses of these two bodies are represented by, say, MA and MB, say MA is the mass of the ball A and MB is the mass of the ball B, then law of conservation of the momentum in all inertial frames holds true. Therefore, using the law of conservation of momentum, we have MAVA equal to MBVB. Let it be equation number 5. Now, substituting the values of the VA and VB here. From this equation, VA equal to d by t0, and from this equation 4, the value of VB is d by t. So this d MA into d by t0 equal to MB into d by t. But time, this t equal to t0 upon under root of 1 minus v square by c square. We put this value here. D by t0 gets cancelled, and we have here MA equal to MB into under root of 1 minus v square by c square, or MB equal to MA upon under root of 1 minus v square by c square. This is equation number 6. Since here, when the velocity v is comparable with the velocity of light c, then under root of 1 minus v square by c square will be less than 1. So the mass MB will be greater than MA. Mass MB will be greater than MA. So initially we have assumed that the rest mass of the both balls A and B are same. But from this equation number 6, it is observed that the mass of the ball B, which is the moving ball, is found to be greater than the mass of the ball which is at rest. And this equation, so if we represent this MA equal to M0, which we call it as a rest mass of the ball, and mb equal to m, which is the mass of the ball when it is in relative motion. By replacing ma and mb by m0 and m, we get the equation as m equal to m0 upon under root of 1 minus v square by c square. Let it be equation number 7. So thus this mass of the body is found to be increasing as the relative velocity of the ball with respect to the relative velocity with respect to an observer increases. So increase in velocity of increase in mass of the body is significant only at the velocities which are comparable with the velocity of light. And this equation number 7, it is called the relativistic formula for the variation of mass with velocity. Let us observe some points. So first, if say this velocity v is very less than c, that is v square by c square will be very small. It will be very small. So v square by c square will tend to 0, and in this case m is equal to m0. From this equation m equal to m0, it means that mass of the body in motion is equal to the mass of the body at rest when the velocity v is very less than c. Then second point is, if the velocity v approaching towards velocity of light, it is comparable with velocity of light, it is comparable with c, then the v square by directly its value of under root of 1 minus v square by c square will be definitely less than 1, as this factor is less than 1, so m will be definitely greater than m0. This means that the mass of the body in motion, for the case when the velocity v is comparable with velocity of light, will be found to be greater than its mass of the body at rest. Then third case is, if say velocity v is very great than is equal to c, say equal to c or v greater than c, then v square by c square will be equal to 1, or it will be v square by c square will be greater than 1, and in this case the mass of the body here, as v square by c square, it tends to 1 minus 1 0, so m will be equal to infinity. M will become infinity or imaginary. So this is not the actual case. Let us stop here. Thank you.